Now, good day, ladies and gentlemen. Today we are going to talk about a Brownian motion. So before we talk about a Brownian motion, we need to talk about a stochastic process, because a stochastic process is influenced by a Brownian motion. So I think it's better if we understand what is a stochastic process before we understand what is a Brownian motion. So what is a Brownian motion? Or at least, or let's say, what is a stochastic process that is influenced by a Brownian motion? We say a stochastic process is a process in which the observed value at each time are random variables, meaning that, in other words, it's a function. You can call it a function. Okay, let's say maybe you call xt a stochastic process, or you can just call it a function of I'm just going to use variable w, which is going to be a random variable. So its outcome of this function f is also going to be a random variable, because it is influenced by a random variable. And in our case, this influence, we are going to call it a Brownian motion. So what is this Brownian motion actually? So in order for us to talk about Brownian motion, let's talk about random walks. A Brownian motion, or let's say a standard Brownian motion in 1D, which we will refer to as a Wiener process. Basically, a standard Brownian motion which is in 1D, a one-dimensional standard Brownian motion, is called a Wiener process. So we say that it's going to start at time 0, and then when it starts, it can go up or down. So it can go up to 1 or down to -1 with 50% probability, right? At each random walk, let's just say it's going to start here again at 1. It can go up or down. So up is going to go to 2, down is going to go to 0, again with 50% probability of going up and 50% probability of going down. The same thing can be said even if you're coming from down here. You can go there with 50% to 0, or down to -2 with 50% probability to go to 0 and 50% probability of going to -1. We call this a random walk, right? So as you can see, now if we were to consider in a random walk, let me try to change the color. So a stochastic process can use this path, or it can take any other path, or it can just continue like this, right? So provided I continue showing the random walks, right, the path it can take is completely random. We don't know if it's going to go to 1 or -1 at first, and if it's at -1, we don't know if it's going to go to 0 or -2, but we do know the probability that it's going to go to -1 or 1 is going to be 50%. So that is how we describe a random walk, and we will say the sum of these random walks, Sn, which is going to be the sum of these random walks. It's going to be n j equals to 1 of these random walks. These are the random walks. Going up or going down is a random walk. We will refer to it as S, right? So this means that the expectation. It means that the expectation of R is going to be equals to what? It's going to be 0.5 times 1 plus -1, because each random walk can go up to 1 or down to a -1 with 50% probability, and therefore it is just going to be 0. And the variance of this random walk, I wrote capital R, let's see if I'm writing var, is just going to be equals to what? I'm going to cancel out everything here. The variance of each individual R is actually going to be what? Is going to be it can be 1.5 times 1 squared plus -1 squared, and this is going to be equals to 1, because you're going to have 0.5 plus times 2, which is going to be 1. and therefore when we can take this further, we can say that the variance of Sn, remember, is the sum of the random walk, is going to be equals to n, because we are going to sum all of them, and the expectation of the sum of the random walk is going to be 0, because you're going to sum the zeros, so it is just going to be 0. So now there's a problem with this model, because it means that it's going to converge to again, we want to increase the number of steps, right? So if the number of steps goes to infinity, it means that this model is going to have a variance which is going to be equals to 0. I mean, like, which is going to go into to infinity. So we need to standardize this process using the central limit theorem. So what do? We are going to say we are going to have a new process which we're going to call the Wiener process, which is going to be our standard Brownian motion, going to time t. Time t is the maturity or the terminal point, and tau is going to be our intervals, or the epochs, as they call them, right? So this is going to be like this. It's going to be the square root of tau times Sn, right? So provided that, okay, we know that this thing is going to start from time 0. Let's say it's going to start from time 0 all the way to time t. It means that if we are going to have equal intervals, we can have t over n, meaning that now our tau is going to be t over n, right? So it means that if we want to find n, if we really want to find n, we can just do this. If we really want to find n, we can just say n is going to be equal to t over tau, right? So instead of writing as n, we can just write the square root of tau as t over tau, right? So actually they don't write it like this. I think I'm thinking too much about a different module. It's going to be n, so you're going to have t over tau. So you can use them interchangeably. So if this is the case, you can try to find the mean. The mean is still going to be 0, because even if you multiply a constant to the expected value, which is 0, then you're still going to have 0, right? So the expectation of this Brownian motion, I mean, like, of this Wiener process, or the standard Brownian motion, is going to be 0, but the variance now is going to have a different property. So you're going to have variance of a Wiener process is going to be equals to so remember that tau, so you're going to have tau, and this thing is going to go to n, right? And we say that it's going to go to n, n, which is going to be equals to t over tau. So you're going to have tau times t over tau, and you're just going to have t. So now we have standardized our process. It's going to have a variance of t. So I hope this makes sense for now. So now, what is the next thing that we can learn about this process, or this Wiener process, is that a Wiener process should always start at 0. Right? We always think and believe that it's going to start at the origin, actually. So it's going to start at the origin, and each independent walk, each increment is independent, and that and also the increment of the process is also going to be independent from each other. So long as there is some time interval between them, and also the Brownian motion, or the random walk, or the Wiener process, is going to have a normal distribution with mean 0 and variance time. right? So if it's going to travel from this time to here, so it means that it's variance. So it's going to have this Brownian motion, or this change of time is going to be, it's going to have like it's going to have normal distribution of 0 and time t. So, and also it is continuous. The Wiener process is also going to be continuous. So these are the properties of the Brownian motion. Examples of Brownian motion, or actually examples of processes that are influenced by Brownian motion. Now, we just learned a Brownian motion. Now we want to learn about functions that are influenced by a Brownian motion, because they do exist. So what are these functions? Let's say can we say that a stochastic process, it's a function, right? So we will just call a stochastic process xt, or you can just say f of w t. So this function is going to be called a stochastic process. So example of these functions can be, let's just say xt is going to be equals to, let's just say a constant, right? Even a constant is fine. It's still going to be influenced by a Brownian motion. It's just that let's just say mu. It's also a process that is influenced by a Brownian motion. It's just that the Brownian motion part, or the Wiener process, it is powered by 0. Therefore, it is no influence. But you can argue that it is a process that is influenced by a Brownian motion. Another example you can think of, let's just say xt is going to be equals to, let's say mu of t, and then you're going to have, say, sigma wt. So as you can see, it is a process that is influenced by a Brownian motion, because here is a Brownian motion, w of t. So this is very important. Another function that you can think of, or another stochastic process that you can think of, let's just say it's going to be equals to e mu minus, let's just say, sigma squared over 2 t plus sigma wt. Even this is a process that is influenced by a Wiener process, or by a Brownian motion. So x of t, it is still a stochastic process, because as you can see, obviously there's w of t over there in the function. It is explicit. You can show that, okay, this function, it is influenced by a Brownian motion. So you can think of another function, or of another stochastic process again, as x of t. Let's just say maybe you can have e minus t to w e to t, right? Even this, you can argue that it is a stochastic process, because it's a process that is influenced by a Brownian motion. But in this case, you have something funny happening down here, right? But don't worry about it. These are just examples. This is beyond our scope. This two Brownian motion up here, this one, you can call it the arithmetic Brownian motion. This stochastic process, you can call it an arithmetic Brownian motion. And this one over here, you can call it a geometric Brownian motion. This one's going to be the arithmetic Brownian motion, right? So we are mostly going to be dealing with the arithmetic Brownian motion. Actually, we are going to be dealing with the geometric Brownian motion. But the arithmetic Brownian motion is going to help us understand, because it's the one which is easy to deal with. So yeah, and this last one is actually going to be called the Onsten. I don't know how to say the name, Onstenville. Okay, fine, sharp. Brownian motion. So it's fine. It is not in our course for now. But anyway, I hope this help you understand the basics of a Brownian motion. So I will make more videos like this. So if you want to have access to them, if you already don't, it means that you don't have priority access. So if you want to join our team, where I make them videos like this, and I give them 3 hours of tuition, and we also have like same test preparation and summaries and more things, actually, you can contact this number on the screen, and then I will let you know how it is done. Or if you have any questions, you can also contact this number over here. So thank you very much. I hope you enjoy your day.